This project started to build a long-range tracking device for drones. Here I have an Egg Timer Mini attached to a 7.4-volt lithium polymer battery. The Mini includes a Maestro A2135 GPS receiver, the beige box, and a specially configured HM-TRP OPRF transceiver module. The transceiver transmits at 915 MHz to a second HOPE-RF module. The NMEA data received by the second transceiver, EggFinder RX, is sent through the white wire from the RxD pin to an RX pin on a yellow board containing an Atmega 328P, which is basically an Arduino Uno. The green blinking LED on the EggFinder RX and the blue blinking LED on the Arduino indicates data packets being received. This data then proceeds via UART connection to a 2102 UART USB bridge, where it ultimately is received as a serial connection on a laptop. The signal transmitting the NMEA data is ultimately a voltage oscillation, so it can be visualized with the dimming and brightening of an LED. When I visualize the data on the laptop through the serial connection, I see question marks. I do not recall exactly what I did. Perhaps it was a misconfiguration of the baud rate. Basically, the expected time to send a packet on the serial connection did not match the actual time. Typical values of this are 9600, 115,200, etc. Could have also actually more likely been the length of the buffer memory specified to hold the MEA data as it comes in. Or both. I believe I used a simple test example with the tiny GPS library to ultimately read in the data. Some of the code for it isn't on the right. I used the RTL SDR to receive FM radio signals. I was also able to transmit to the RTL SDR at 915 MHz using the Lime SDR Mini. You can see the spectrum plot, the rapidly moving white jaggy lines at the top, and the colorful spectrogram, or waterfall, at the bottom. Here is the GNU Radio companion sketch for the FM radio transmission provided by Myriad RF for the Lime SDR Mini. I thought that I was going to configure the Lime SDR Mini to send my LoRa data, but it ended up being much easier to use the LoRa devices provided by Heltec Automation. I have the ping pong example using two Heltec cube cells transmitting over LoRa. Here I am visualizing LoRa transmissions with the GQRX software and an RTL SDR. I also have two Heltec modules that combine both Wi-Fi and LoRa. Both of these can receive signals from the cube cells and can serve as a bridge to a Wi-Fi network. Using one of the provided examples, the simple Wi-Fi server, I am testing the Wi-Fi capability of the Heltec Wi-Fi LoRa ESP32. Two white Heltec LoRa Wi-Fi ESP32s are receiving from a green Heltec LoRa cube cell dev board. In this example, I ran the default LoRa sender code example for the Heltec cube cell dev board. Make sure that the set frequency is 915 MHz, not 868 MHz or something else. This is for the US. The allowed frequency for these IoT type devices varies by region. This is a BH1750 digital light sensor on a debug board, both provided by Heltec Automation. To hook it up, I followed the pinout as well as the silk screen on the board for the Heltec cube cell linked to earlier in the video. At first, I had the cube cell connected directly to serial for debugging, and then the BH1750 on the Heltec cube cell is transmitting to the Heltec Wi-Fi LoRa ESP32. The Heltec Wi-Fi LoRa ESP32 is connected via serial to the laptop, so the Wi-Fi capability is not being used. I can put my hand over the BH1750 digital light sensor and see the number change on the OLED display on the Heltec Wi-Fi ESP32. Combine the BH1750test.ino with LoRa sender.ino HealthTech code examples with modifications to send the sensor data over LoRa and run them on the cube cell. Take the OLED receiver code example and change the band to 915 e to the 6 or 915 MHz. I can extend the OLED receiver code to write the sensor data to a web server accessible by laptop. Unfortunately, the data is only updated when I do an HTTP GET, so this will be redone with WebSockets later. To test writing the data to a database instead of the browser window, I set up a PHP script that takes whatever value of lux a user passes as an argument to an HTTP GET and writes it to a MySQL database. I think someone from the Techlahoma Slack mentioned WebSockets when I wanted to continually get data from the sensor as it was available. The Abley article, linked to below, mentions, in my words, WebSockets as a means to maintain a full duplex persistent connection between two agents after an initial HTTP handshake until connection is closed. The example you are seeing above is from Sean Heimel. The black box has output from a Python client in the example. The interaction with this and the browser WebSocket clients will be apparent in the dev TTY USB 0 serial output. This is the second example from Sean Heimel, which involves blinking of an LED with a WebSocket server. Unfortunately, the code has no way of checking the state, only remembering what happened, so it must be modified. WebSockets are better than HTTP GET used earlier, which makes a request, but then closes receiving no more data. This is why I had to refresh the browser whenever I wanted to see new data. In reality, I wanted to see new sensor data whenever there was new sensor data. The blinking LED example also involved a soft access point, which meant it was not on my router's network, but I was able to modify it so it was. Here is the device, and following, here is the code that I had for that. Around this point, I realized that this approach was not going to give me the data from a sensor if it was realized in place of the LED, because I was pushing commands to the device rather than pulling information from it. When I thought of two-way communication, I thought of a chat app. Thankfully, WebDev Simplified offered a version with Socket.io that I was able to follow and build. The browser acts as a client, and code is written on the server in such a way that messages sent by any client are broadcast to all. I did like this since I could see a sensor in place of sending quote-unquote chat messages. Unfortunately, it used Socket.io, which I found was incompatible with standard WebSockets. I continued looking for examples I could easily modify to aid my weak understanding. I then started looking for WebSocket clients and servers for the Arduino platform. I found Tech Tutorials X. It offered both a client and a server that would test and work together. I tried getting Marcus Settler's Links 2004 library to play with Morganser's ESP8266 WebSocket library. I was getting errors with running Marcus's code. Moreover, it was generally a bad time. I learned 0.0.00 where IP address was bad. Following the stack trace tells me about issues with the WebSocket loop. Removing this removes complaint, but fixing it requires a few more lines of code that we'll be showing next. It turns out that I was setting the code up incorrectly. On the server side, I see connecting to Wi-Fi, connected to the Wi-Fi network, 10.0.0.8, calculating, sending. Then comes the client. This is one crazy Marcus client. Then I get a bunch of random numbers from the client. Here's the server-side code. On the client side, when I fix my code using Marcus library, I see connecting, connected, my IP address, 10.0.07, random number is 909, random number is 22. I ended up modifying the ESP8226 shop example using the Node.js WebSocket server on my laptop and a WebSocket client on the Heltec LoRa ESP32. You will see more development in the next video. During my exploration stage, I drew LoRa devices talking to a gateway. The Node.js server in the ESP8266 shop tutorial could be like a gateway. Node.js could be preferable since I may have multiple threads getting data from the sensor, parsing it and inserting it to the database. I would like to find out if I could follow queues from the Meshtastic project and process data from multiple sensors on the same frequency but different public keys. To process the data from the sensors on the ESP32, I could try using the dual core capabilities as well as proto-threading. MQTT could help with power consumption, but not now. I just caught a fish. I receive all LoRa traffic, not just mine. I can hook up a cryptographic chip to sign all my messages and then use a public key to verify them. This will help me know who the message is coming from. However, even though a cryptographic chip will provide a public key, I will still find it difficult to authenticate the public key from the crypto chip. That is, I may find it difficult to verify the public key is from the crypto chip. I may try placing the key on a ledger or a public key registry. When I was researching this, I had both Occam and SparkFun's ATEC 508A crypto chip protoboard in mind. I wanted something I could get off the ground with, so I began with the SparkFun board. Then I looked at Occam's config ATEC 508A.py file to inform my configuration of the SparkFun library. I found that Occam utilized the ATEC 508A manufacturer C library CryptoAuth Lib and was inspired by the Python library CryptoAuth tools for the config ATEC 508A.py file. I initially tried to get the config ATEC 508A.py file to run on the ESP32 using MicroPython, but I found out there was not enough memory. There are 16 megabyte versions of the ESP32 that may have worked better, but I only had a 4 megabyte version. I also tried flashing the configuration directly using the ESP IDF tools, but it grew very confused. I recalled that CryptoAuth Lib was not very beginner friendly. I did find a datasheet for the ATEC 508A and that was very helpful. I managed to get Occam's configuration on the SparkFun board, but I realized later that to start out with SparkFun examples written by Pete Lewis. Lewis's examples were a lot easier to use, and he even got the first example to run on my yellow Arduino Uno clone. Pete Lewis's example utilizes asymmetric key cryptography. There is a wonderful introduction at techtarget.com. The full data sheet for the ATEC 508A is available on SparkFun's website. It was through this sheet that I could look up opcodes and the meaning of the configuration file. I needed a way to convert bytes expressed in hex to binary numbers. I wrote code in C to convert hex numbers to string representations of the binary equivalent. Here you can see modifications that I made to the SparkFun example to emulate the config ATEC 508A.py file. Unused, but its end-to-end communication technique may be superior. This will be discussed in a later video.